Thanks for coming to our second iteration of the STIG webinar. Today we have two great talks lined up for you. Our first is going to be from Dr. Martin Cordiner at the NASA Goddard Space Flight Center. Martin Cordiner is a research associate professor at the Department of Physics, Catholic University of America. His PhD in astrochemistry was obtained from the University of Nottingham in 2006. He now works as a full-time researcher in astrochemistry and planetary science at the NASA Goddard Space Flight Center in Greenbelt, Maryland. Dr. Cordiner's research aims to understand the chemistry and physics of solar system bodies, interstellar clouds, and circumstellar environments using a combination of ground and space-based observations combined with detailed computer simulations. By studying the origin and evolution of matter from interstellar to planetary phases, this work helps inform our understanding of the chemical conditions that led to life in the universe. Today, he'll be talking to us about phosphine in the atmosphere of Venus, a sensitive upper limit using SOFIA and GREAT. And so with that, I will stop sharing, and Martin, take it away.
All right, thank you very much, Nathan. I'm just sharing my screen here. Okay, can you see that okay?
Yes.
Let me just maximize. All right. For some reason I've got a top bar on there. That doesn't usually happen. Oh, there it is. All right. So yes, thank you very much, Nathan, and thanks very much to the organizers of this seminar series for giving me the opportunity to present this research, which is by myself and some other fine co-authors you see listed here. I also present some new ALMA results on Venus at the end of this talk if I have time, but that's at a rather more preliminary stage than I was expecting because of being moved up the program by a couple of months. I just want to also say what a joy and a pleasure it was to have the opportunity to use the SOFIA aircraft and do observations last year. It's really a unique and amazing telescope, and to finally get some observing time on it after a few years of putting in unsuccessful applications was a very good thing. So this work that I'm presenting here is now accepted for publication in Geophysical Research Letters. You can find that paper on the AstroPH server if you want to have a look at more of the details. So phosphine on Venus, this came to the public attention in quite a big way in the mid part of 2020 when a paper came out by Jane Greaves et al. Claiming a detection of the phosphine molecule in Venus's atmosphere. It's a relatively simple molecule, phosphorus atom with 3 hydrogens, you see in the top right. And in planetary atmospheres, you can envisage possible production mechanisms for this gas through sort of conventional photochemical processes in the atmosphere. Venus, of course, is a unique body in the solar system with its very dense atmosphere that seems to be largely dominated by volcanic gases. So you could postulate that phosphine is coming out of volcanoes, and that's actually reasonable to assume, or maybe not the phosphine itself, but phosphine precursors at least could be volcanically outgassed and converted to phosphine in the atmosphere. Other meteorological phenomena such as lightning could also produce certain amounts of phosphine. However, as was identified in this paper and other studies, phosphine is actually quite difficult to synthesize in terrestrial type planetary atmospheres. So in the absence of sort of effective production pathways, you might end up coming to more fanciful hypotheses, such as the possibility of life producing the phosphine, which is not completely outlandish because of the fact that in our own planet's atmosphere, most of the phosphine that we observe is actually produced by life. So study of phosphine as a possible biomarker is still in progress, and its efficacy for use as such. So it's very interesting to study phosphine in planetary atmospheres and also on Venus. So this is a spectrum from the JCMT telescope on the right and the ALMA telescope. And these are the observations from the Greaves et al. Initial detection paper, where you see a sort of tentative signal in the JCMT spectrum. This is of the phosphine J equals 1 to 0 transition that they targeted in the millimeter wave. And the ALMA spectrum is the lower one and seems a lot more convincing. However, there were subsequent follow-up studies, and immediately, because of the impact of this result, it was interesting to dive into the archival data, which were publicly available, and have a look at the data itself and see if we could extract a similar signal. We immediately determined that there was some problems with the calibration of these data, and they needed to be recalibrated. And in fact, the Greaves et al. Team came back with their recalibrated. This is a disk average spectrum that you see here in green, and the signal is obviously a lot smaller after the recalibration. And in fact, members of our team had a look at this data. Myself, Imke Tepeta, and Brian Butler did independent analyses, and just trying to go through the standard data analysis procedures that we would do for any ALMA data of any planetary body. And we were unfortunately unable to reproduce the phosphine signal there. And the conclusion, and this is published in the Villanueva study in 2021, and the conclusion of that study was that we could only obtain basically an upper limit for phosphine based on these data. Other follow-up studies using IRTF data, the infrared telescope on Mauna Kea by Encronaz, and also using Venus Express solar occultation spectra in the infrared, further failed to detect any phosphine. So this became then an interesting debate in the literature and online and on Twitter, and a lot of back and forth was going on as to whether phosphine was really there or not. Interestingly, if you want to really get high sensitivity on this kind of gas measurement, it would be ideal to have in situ measurements. And in fact, the Pioneer Venus mass spectrometer went down, it went down on a probe in the 80s. And if you have a look at that data, you may be able to convince yourself that there's some evidence for phosphine in that data, but it's somewhat marginal because this phosphine mass peak here that you see re-examined by Mogul et al. 2021 actually overlaps with H2S plus peak. So it's a bit difficult to disentangle that and get a conclusive result from that. So the debate continues anyway, and the Greaves et al. Team are still very sure that they've detected phosphine and are doing some follow-up observations with JCMT and reanalysis of the ALMA data themselves to convince themselves that it's there. Just as a sort of aside to this, I attempted to reproduce the latest version of the spectrum using the ALMA data, and I was only able to kind of get, well, it's kind of cherry picking the data to go for the sort of maximum possible signal, and removing certain baselines from the data and flattening it with a certain order of polynomial. And I still wasn't able to get anywhere near this level of detection that they're currently claiming. So it's a challenge. It's a challenge to see if phosphine is really there or not. And so therefore, it's good to look to other telescopes and see if we can detect different spectral lines in this region. And so I looked to the SOFIA telescope, which is the Stratospheric Observatory for Infrared Astronomy. It's an airborne telescope, really unique facility, hole in the side of the Boeing 747 where the telescope pokes out, and you're able to gather light from extraterrestrial sources from above the atmosphere. So you're not so obscured by basically the terrestrial contamination and atmospheric opacity that really plagues these high frequency regions where the phosphine lines are found. So we were able to target phosphine at 534 and 1067 gigahertz in this sort of submillimeter terahertz range of the spectrum that SOFIA is very sensitive to. And there's the J equals 2 to 1 and 4 to 3 multiplets. So we can target multiple transitions of phosphine in this region. We had 3 flights successful on the 10th, 11th, and 13th of November last year. Only about 36 minutes on source because Venus was actually very low in the sky, and we were already chasing it down immediately after sunset. We had to open the telescope, and Venus was setting rapidly, so we couldn't get that much data. But the precipitable water vapor burden was very low, and yet weather conditions were excellent. So here we see a picture out of the window, and we've got the crescent moon up here as we flew out of Palmdale, flying over the Los Angeles coastline, and there's Venus there, that little dot. And here's the inside of the spacecraft. And of course, we're all observing the COVID-19 strict protocols at that time. So yeah, it was a fun flight. Unfortunately, the data wasn't quite as good as the weather conditions might have led us to anticipate. There's strong atmospheric ozone absorption lines. It's not totally unexpected. There's still some atmosphere above you, and you're observing towards a strong background continuum source. So we see these deep ozone absorptions in the spectra. Superimposed on the Venus continuum is also, unfortunately, a rather strong standing wave ripple due to internal reflections inside the Great and the SOFIA optics. And you see the phosphine lines marked here. So we have to do some cleanup on these data to get them into a state where we can do science. But the fact that these are quasi-periodic signals means that we can use basically frequency component analysis to try and clean these up in an unbiased way as we can. So what the aim here is to reduce the amplitude of these continuum ripples without destroying any phosphine signal that may be present. The technique that we settled on is a less destructive method than doing an FFT and knocking out loads of frequencies with uncertain phases and amplitudes. We use a Lomskagel periodogram analysis where you actually take a sweep through a range of possible frequencies that you think may be present. And it's like a cross correlation as a function of frequency. So here we see in the top left, the baseline subtracted spectrum, and then the periodogram where these peaks, sorry, the font's a bit small. I had to cram lots of figures onto this plot. But basically, these peaks represent the frequency components present in the spectrum. And then we take that frequency, we allow the amplitude and the phase to vary, and then subtract it off. And we iterate that procedure. We redo the periodogram and we iterate, and we keep subtracting periodic fringes, and you see the baseline get flatter and flatter. So these periodic frequencies are well defined at each step. So we're confident at each step we're just removing one frequency component from the data till we end up with no clear periodic signals remaining. I should also note that we mask the region around the putative phosphine lines so that we don't try to end up fitting any signal that may be there. We did this in the two 4-grade channels, the 4G1 and the 4G2, and went through and subtracted off those periodic frequencies. And then we add back the fitted continuum from the earlier step so that we can do some spectral modeling. The spectral models are non-trivial. Of course, Venus has plenty of different gases in its atmosphere, water, carbon dioxide, carbon monoxide, sulfuric acid, SO2, and others. And we take the reference atmosphere from the planetary spectrum generator, which is primarily based on the Ehrenreich 2012 compilation, and we take the Vera reference atmosphere temperature profile, which you see on the left, and these reference abundances on the right, and then we set phosphine abundance. And what we're trying to do is to generate an upper limit on phosphine. It's a lot of effort to go to generate an upper limit, but it's worthwhile to see if we can get the most reliable value that we can obtain and make the most out of these data, which are really quite a unique data set in this frequency range. So we start off with a continuum, but it's not exactly a continuum because there are telluric lines superimposed. Here I've marked some ozone lines, which are superimposed. And basically there's 0 parts per billion phosphine model in blue, which you could see, and it has those telluric components in there. And that's fitted to the continuum. And then we successively increase the phosphine abundance in the model and monitor how the chi-square value changes. What we see is the chi-square value increases with abundance. That means that the fit gets worse and worse as we go up, but we get to a point where we can define confidence level, confidence interval, and we put a 99% confidence limit here, and then we can read off the abundance, and that corresponds to a phosphine abundance of 0.8 parts per billion, assuming constant with altitude. There's not really much point trying to fit more complicated vertical profiles than that. And this is obviously dramatically lower than the 20 parts per billion initially claimed by the Greaves et al. Study. Similarly, for the 4G1 channel, the lines are actually a bit weaker in this channel, and there's only 2 of them, so we're not able to get such a strict upper limit in this channel. But again, no detection and 7 parts per billion upper limit from the 4G1 channel. Just as a little sort of insight into the degree to which our defringing strategy, this sort of de-rippling iterative procedure, we can basically fit the same set of fringes to a model spectrum. And so here we see a model in blue before the de-rippling strategy, and then we subtract the exact same 7 sinusoidal frequencies from that model. And that's shown in orange. And you see that, yeah, there's some distortion of the continuum, but the basic spectral lines are largely unaffected by our ripple reduction strategy, and the residuals are down at the bottom, which is significantly less than the noise level in these spectra. So that's encouraging that we're not being too destructive in our analysis of these data. When we remove these ripples, we're reasonably sure that we're not removing real signal. One of the nice things you can do once you've gone to the effort of making a detailed radiative transfer model for the spectral lines of interest, you can plot a contribution function. And what this shows you is, as a function of frequency and altitude, the amount of absorption in this case, which is present from these phosphine lines. And here you see the quadruplet of the J = 4:3 phosphine transition that we targeted. And what the model is showing us is that in the narrow line components that we're sensitive to with this very high resolution SOFIA great spectroscopy, the lines only start to become distinguishable from the broad continuum. You know, this is quite zoomed out here. If we zoom in, then what we see is that the lines blend into the continuum at an altitude of about 75 kilometers. And the narrow components of these lines are really sensitive to emission from this like 80 to 110, 120 kilometer range. So this is quite high altitudes that we're probing here, and is actually significantly above the cloud tops. I'm not going to show it here, but we've also calculated the contribution functions from the J = 1 to 0 transition that Greaves et al. Observed when they claimed to be observing the cloud decks of Venus in their original study. And actually, as a result of the high spectral resolution here, you're really, with this kind of heterodyne millimeter, sub-millimeter far infrared spectroscopy, you're really only sensitive to high altitudes above the cloud decks. So this sort of above 75 kilometers, you know, we're in some of the upper haze layers still, but you certainly wouldn't say that we're sounding the cloud decks with this technique. So it's quite high altitude. So I'll just conclude this part of the talk and say, you know, the initial claims of phosphine on Venus, in my opinion, remain highly questionable. And if you go by the number of studies refuting the initial claim now, it seems like the evidence is falling down against phosphine being present. So yeah, SOFIA, great far infrared observations. As I said, it's quite sensitive, in fact, very sensitive to phosphine in the upper middle atmosphere. Unfortunately, there's still baseline ripples in this kind of data because of standing waves in the instrument. But it's, you know, we think that we did a reasonably good job of removing those using the periodogram analysis to get this upper limit. So it seems like the Venus alien hunters are going to have to go back to the drawing board on this one. And there's still no good evidence for Venus, for phosphine on Venus, in my opinion. What this study does prove, you know, beyond doubt, millimeter wave far infrared spectroscopy is a sensitive probe of astrobiologically relevant molecules in planetary atmospheres. You have a really bright background source, like with a planet, and that allows you to do absorption spectroscopy at very high sensitivity. But to be able to do that, you have to be able to have a smooth baseline. You either have to be able to do a great job of your baseline fitting and correction, which is difficult, or find ways to mitigate baseline ripples in the instrument. And I think that moving forwards, you know, this technique can be very powerful for planetary remote sensing. We need to work on ways of mitigating those baseline ripples in the observation, either through calibration procedures, or improved reflection reduction when we're designing these kinds of instruments for planetary science. Just in my last few minutes, I will talk about the future. So as people may have heard, Venus is a really hot topic in terms of planetary missions at the moment. NASA recently approved the funding for 2 new missions to Venus, the Da Vinci Plus and the Veritas. So Da Vinci Plus primarily sounding the atmosphere, whereas Veritas is doing observations of the surface to try and search for signs of volcanism and explore the geology, the Venusology a bit more. Meanwhile, ESA is going to be launching the Envision mission. The Indian Space Agency is well on the way to getting their Chakrayan-1 Venus mission ready, and also coming out of China is going to be the VOICE mission. And as far as I'm aware from seeing the talk at COSPAR this summer, this VOICE mission may be flying a heterodyne spectrometer similar to get spectra similar to the sorts of ones that we obtained with SOFIA. So that would be quite exciting to get that in situ look at Venus's atmosphere at high spectral resolution to see what gases may be there. I've been doing some work with ALMA in the meantime. So I had a Cycle 8 program for the ACA, the Atacama Compact Array, which is the sort of smaller component of ALMA. It's a bit easier to get time on, but it also has a larger beam size, which is in many ways better suited to observing Venus, at least if you don't want to do mapping. It's very well suited to observing Venus. The beam size is about 7 arc seconds compared to 10 to 30 or so arc seconds for Venus. So I was searching for more gases related to the phosphine chemistry. It's plausible that phosphorus on Venus is coming out of phosphoric acid, which could be a volcanic gas, and was inferred to be present based on the Russian Vega Lander X-ray spectrometry, which was done in the 80s, in one of their in situ probes. And if you have phosphoric acid and react it with hydrogen, you can pull out successive OH molecules to produce water and end up with PO. So it's interesting to search for PO, and this is a species which appears in the submillimeter wave with strong rotational transitions. PS, if you react PO with H2S, you should be able to produce PS as well. So we can probe this phosphorus chemistry with observations, and here you see some spectral simulations. I also went after some more exotic molecules, which may be highly speculative, but given the analogy with iovolcanism, if volcanic outgassing is occurring vigorously on Venus, you may also expect these kind of alkali salt vapors, the sodium chloride and potassium chloride. If we could detect those, then that could be a smoking gun for active volcanism, which is kind of elusive on Venus. So we obtained some observations this year, and I've just been observing. I've just been looking at this data in the last few days, the last week or so. And
hey, Martin.
Yeah.
Just letting you know you have 5 minutes before we need to move to questions.
Yeah, sure thing. Thanks, Nathan. So yeah, here's the ACA results, the Atacama Compact Array image of Venus. So Venus, there it is, nice and bright in the middle. Always good to have a nice continuum image, even if it's largely unresolved. And we observe 4 spectral windows that you see on the right. And unfortunately, from my preliminary analyses, this is very preliminary, I'm not seeing a whole lot of anything there. I'm seeing telluric emission features. I'm not quite sure why they're appearing in emission, but these coincide with the frequencies of terrestrial ozone. So not much there in the ACA data. Unfortunately, this data is much more noisy than we actually planned on. So again, it comes down to difficulties with the calibration. Just like with the Greaves et al. ALMA data, these ACA data are quite difficult to calibrate. And we're talking about baseline calibration. It's analogous to optical flat fielding, where you need a calibration source. In the optical, you use a flat field lamp to cancel out those pixel to pixel variations in absolute sensitivity of your instrument. But in the submillimeter with interferometry, we don't have access to a flat field lamp, and we have to use a solar system flux calibration target, which is preferably a point source, usually a small moon or an asteroid or something like that. And that tends to be a lot fainter than our Venus continuum. So it's very difficult to calibrate this kind of data set using that method. The total power data is interesting. It's actually, I think, more interesting. Also difficult to calibrate. There's a lot of wiggles and baseline ripples in this data, but this is using the 4 standalone single dishes from the ACA, and the image is even less well resolved with our like 30 arc-second beam from the ACA total power, and the spectra on the right. They're quite ripply, but the dynamic range of these spectra is actually getting up to the level that we asked for in the proposal, because this is, you know, a simple on-off sky calibration, which does a better job of cancelling out the pixel-to-pixel variations in gain. But we do end up with some ripples in the data. These ozone lines stand out, but I'm going to look at these data soon and try and get some robust measurements and do a proper search for these features once I've done some de-rippling and see if we can clean up the baselines and get some upper limits for the species we're looking for, the PO, the PS, and these alkali salts. That'll be quite exciting. You know, I can try and clean up these ACA data with a bit of bandpass smoothing. That's the common technique. We smooth out the spectrum of the bandpass calibrator, but that has its own set of problems and can actually introduce more ripples. So yeah, how to mitigate these ripples is something that we need to think about seriously in future to do this kind of work. So yeah, I think I'll leave it there, and I'm happy to take any questions if there are any. So thanks a lot for listening.
All right, thank you, Martin. If there are any questions, can you use the raise your hand feature and we'll call on you. Meredith, oh no, sorry, that's applause. Yes, Candace.
So if that what appeared to be an absorption feature is not phosphine, what possibly could that source have been that the Graves data was seeing?
Well, it depends how you cut and slice the data. As far as I'm concerned, in this original ALMA observation, there's no good evidence for there being a line there at all. It's the bumps and wiggles. I didn't show it in this talk because of lack of time, but if you dig into the data and look at the kind of image cubes and you move your mouse around, you see that this data is subject to a large amount of bandpass artifacts. And if you cancel those out in just the right way and fit just the right order of polynomial, you can sometimes get it to reproduce a signal a bit like this one that you see, or maybe like this one. From our analyses, as I say, there were 3 different people in our team looking at this independently. We weren't able to see any signal there. That doesn't say anything about the JCMT data. That was actually looked at by Thompson, 2021, as a follow-up to the Greaves tentative detection. And as far as I know, the Greaves et al. Interpretation of this JCMT spectrum is that it's a tentative. But if you, I think there's basically issues with polynomial fitting in this data as well. You have to fit a lot of different functions to the baseline to get to flatten it out. There's always a risk of introducing spurious features when you do that. So I don't really, I haven't looked at the JCMT data myself, but I'm not completely sure that there's a significant detection there either. There is also an SO2 line that overlaps this frequency, but it's kind of a weak one. So there is that as well.
All right, we have a few more minutes if there are any more questions.
I have a quick question. Sorry, I couldn't figure out how to raise my hand. I apologize. Something about the co-hosting. It's moved the hand raising. So Martin, this is really super interesting, and it seems like the baseline ripple poses a huge issue going forward for searches for spectroscopic signatures of chemistry in Venus or in protoplanetary disks or something like that. So are there good methods, you think, for doing accurate bandpass calibration that could could obviate this, because from an instrumental standpoint, you're not going to get rid of the ripple. It's quasi impossible to do. So what could be done on the calibration side to get rid of it?
Well, one of the reasons it's so difficult to mitigate in the SOFIA great data is that it's dual sideband observations, and the two sidebands are superimposed. There was some hope we'd be able to do a sort of a ripple removal without having to go to the extent of doing all this periodogram analysis. But once you've overlaid the two sidebands like that, the ripples start beating and interacting. It becomes very difficult, and there's a few frequency terms in there from the different internal reflections. And as you say, it's difficult to remove those. And once you've got different gain levels in your different sidebands, it becomes very difficult to calibrate those out. One suggestion that probably would have helped with the SOFIA data, if we had observed another bright flat spectrum calibrator at the time of the observations, then we could have calibrated those gain terms a bit more reliably. So if we'd maybe observed the moon, something like that. And as far as the ALMA data, it's not a lost cause for calibrating these interferometric observations. You just need a bright enough calibrator and spend long enough on it. So if we observed Venus for half an hour, if we observed the calibrator for a couple of hours, say, it just depends. Building up the signal on the calibrator is really the key. So doing custom calibration scans, I think, is the secret there.
All right, well, thanks, Martin. If there aren't any other questions, we'll go ahead and move on to our next speaker.
All right, thank you very much.
All righty, so our next speaker is Dr. Thomas Lai. Thomas is a postdoctoral scholar research associate at Caltech IPAC. He is interested in dust physics and in understanding how star formation and AGN impact the ISM properties. Today, Thomas will be talking about AGN feedback on the star-forming ISM and NGC 7469 with JWST. And Thomas, if you could go ahead and start sharing your screen, I'll let you take it away.
All right, yeah, thank you, Nathan. Let me see if I can share. Can you guys see the slides?
Yes.
Right. Yeah, great. So yeah, thanks for coming to the talk. And I'm now a postdoc at Caltech IPAC, working with the ALMAS and the GOES team. And today, I'd like to share my journey of the past 3 to 4 months on working on the JWST ERS observations, in particular on an interesting C4 galaxy, NGC 7469. And our results has recently been accepted in APJ letter. So if you're interested, I also have the archive numbers here. You can go and check out our paper. And I'd like to shout out to all of my amazing colleagues, collaborators, and who may also be in the audience as well, and for making this work happen. All right, so first, I will have a brief introduction about our ERS program, and later on, I will focus on our observations on what we found so far on this interesting C4 galaxy, NGC 7466. All right, so Our NGC 7469 JWST observation is carried out from the Early Release Science Program 1328. And the goal of the ERS program is to realize the JWST's full science potential and to help the science community to quickly learn how to use the JWST instruments and its capabilities. In our program, we focus on resolving galaxies, which are mainly drawn from the gold sample. So here I show the 4 targets that we have for this ERS program. We'd like to use those sample to study the physics of star formation, black hole growth, and feedback in 4 nearby merging luminous infrared galaxies. And with the JWS observation of NIRCam, NIRSPEC, and MIRI imaging together with the IFU spectral data, together with all the other ancillary data that we had from our team, we would like to study the stars and the properties of stars together with gas and dust on a 50 to 100 parsec scales. So the deliveries of this ERS program includes the Cafe spectral decomposition tool, which I will be talking about later on. Also the line maps and the ancillary data. So in total, our JWST observing time is about 28 hours. And so far, we're still in the process of acquiring our data, but there are some of the amazing images that I'd like to share with you now. Yeah, so those are the images from NIRCam and MIRI that we had so far. So comparing to the HST images, as you can see here, it's really amazing that from JWST, we're able to look into peek inside the dust and then see the amazing features of those star forming regions. For example, if you look into this galaxy 23T96, you see that in the HST observation at this region, it's obscured. We couldn't really see that much of light. However, in the infrared, we see that there's a blooming of infrared light in this region, which we're really interested in studying at. Yeah, and also, like in the galaxy that I'm going to talk about, 7469 today, we see that from the NIRCam image, there's a beautiful star-forming ring at the distance of around 500 parsec with a Seyfert 1.5 nuclei at the center. So yeah, these images, some of them I took it from the Reddit. So a lot of amateur astronomers are also really interested in those JWST observations. That since the ERS is mainly public, so I mean, a lot of people kind of just look into all those beautiful images and then make their own amazing maps, amazing images, as you can see here. So far, we already got 2 IFU observations together with 3 galaxies that we have images, and we're still waiting for the observation of 3256. So please stay tuned for the data of this galaxy. It's going to be amazing as well. So yeah, we're all really looking forward to it. So here are some of the questions that we'd like to answer from our ERS program. It's on how stars and black hole evolves in mergers, and also how those systems affect its nearby ISM. And also we're interested in understanding the fueling and feedback processes in those systems. And so with the huge leap of the spatial resolution in JWST, we will be able to study the ISM of nearby starbursts and agent on a sub-kiloparsec scale. And this will allow us to have a close look at one of the most abundant molecules in the universe, which is the polysaccharide aromatic hydrocarbon in those amazing merger systems. Yeah, so first of all, why study PAHs, which I may refer to PAHs later on in my talk. And because we actually live in an aromatic universe, PAHs contains up to about 50% of the cosmic carbon, and it also contributes up to about 20% of the total luminary infrared luminosity. And it also dominates the heating of the neutral gas through photoelectric heating, and it also governs the energy budget in the ISM, so that in turn it will impact the star formation. And also PAHs are pretty bright, in fact. Yeah, so here are several important metal cooling and recombination lines. As you can see here, the y-axis is the luminosity of the line compared to the total infrared luminosity. But if we compare those lines with PAHs, PAH emission is just so luminous that it outshines other resolved emission bands. So actually, 5% of all the non-primordial radiative energy in the universe processed through PAH grains. And in comparison, the next strongest cooling line in the galaxy is C2, which is only about 5% of the PAH luminosity. Yeah, so since PAHs are so bright, we can they can be well studied in the high redshift world as well, especially in the JWST era. So here I have this plot, including several of the JWST selected filters together with a typical PAH spectrum in the star-forming galaxy. And this shows how PAH bands may shift with respect to the redshift, allow us to probe the star formation or dust evolution in the distant universe. So one thing that really makes PAH useful is PAH can serve as a useful probe for the local physical condition. So the spectrum shown here are a typical PAH spectrum in red, and PAH bands are at different wavelengths arise from different vibrational modes. As you can see here, some of them are in CH stretch modes, and some of them may be in in-plane mode, and some of them may be in out-of-plane modes. Also, the hardness of the UV radiation field in the environments lead to different ionization state, as you can see from the right panel, which in turn, this will change the overall appearance of the PAH spectrum. For example, for neutral PAHs at 3.3 and 11.3 is relatively stronger, whereas for the ionization PAHs, emission between 6 to 9 micron are brighter. So in addition to PAH, there are other key diagnostics we can find in the mid-infrared. Like for larger grains, we can see a silicate emission at 9.7 micron together with 18 micron. And also those large grains sets the continuum of the spectrum in the mid-infrared. And also we can see a suite of different H2 rotational lines as I listed here, and also some recombination lines and various line emissions, for example, neon 2 and neon 3, which we typically use the ratio to use it as a probe for the hardness of the interstellar radiation field. And lastly, we can also find some ice absorptions in the near infrared regimes, like what we show here, the ice and CO2 and CO absorptions. Yeah, now I'd like to dive into our NGC 7469 observations to show you what we've learned so far. And excuse me for a bit. Yeah, so NGC 7469, it's nice laboratory for study the AGN and starburst connection. It has a CFER 1.5 nucleus together with, it's also in a galaxy pair that has a companion IC 4283 at a distance of about 70.6 megaparsec. And 7469 hosts both an accreting black hole and a circumnuclear starburst ring at about 1.5 arcsecond, and also has highly ionized outflow from the nucleus. And the star-forming ring consists of two distinct stellar population of young and medium age. So I'm referring to a paper from Thomas Spahn here, 2022, which is also in the archive, as you can see here. In this paper, we have used multiple photometric images and then to identify star clusters in this galaxy. So if you're interested in that, you are welcome to look into this paper. Yeah, so the first thing that we get this JWST spectrum, we're really excited to see the difference between what we get from the JW and also from what we got from Spacer IIS. So here I show the slit of the Spacer IIS together with the spectrum. We see that there's a prominent pH feature here. And for the JWST observation, I'm particularly interested in the IFU observation, which includes a region of 3 times 3 arcsecond region here, focusing at the center and the starburst ring. Yeah, and this is what we got from our IFU observation. So we clearly see that with a spectral resolution that's about 30 times better than Spitzer, we're able to identify way more features here from our spectrum. All the emission lines are sharper. And for example, at the 7-micron regime, we see here, we see this is the comparison between the Spitzer and the JWST. So like I've been spending quite a lot of my time in the from the IRS data to separate this S5 line with the argon-2 lines. And it's pretty hard given the data that we have from Spitzer. However, right now with the JWST, it's really easy to do these kind of deblending of the observation of the emission lines. Yeah, so with this high spectral resolution, we can also create line maps from those lines without any ambiguity caused by blending, and to study the gas dynamics in those galaxies. So yeah, I will refer you to read this paper from Vivian Yu, which in this paper, we also show beautiful line maps. As you can see here, those are iron line and H2S5 line and argon-2 line maps here. With those line maps, we're able to study the outflow dynamics in the vicinity of the supermassive black hole on the very center. And so if you're a shock or feedback enthusiast, you're gonna enjoy this paper. And in this paper, we also have a detailed discussions on the geometry of the outflow in this galaxy. So yeah, if you're interested, please just look into the archive numbers here. Yeah, so while in Vivian's paper, the focus is more on the gas dynamics. In my work here, I focus more on the dust and gas properties in the star-forming ring. So in this study, we're using an aperture-based analysis, and I'm placing those apertures based on the 6.2 pH map that we acquired with an aperture size of a radius of 0.4 arcsecond. Yeah, and one thing that I'd like to point it out that the cube that we're acquiring here, it's basically all within the Spitzer IRS slit. So that's saying with the spatial resolution from JWST, we're able to really probe the very center of this galaxy and then to isolate the star-forming regions from the central AGN. So the first thing that I did is to place 11 apertures along the star-forming ring because I'm interested in study path variation in the ring regions. And later on, we also put in additional apertures that goes in the radial direction so that we can study the variations in the variation between like the star-forming clumps when we move our apertures towards the center. We'd like to see the changes of those dust and gas features. And lastly, the purple circle just shows another aperture that we have for the extraction of the nucleus spectrum. But yeah, here are the 18 spectra that we get from our study here. I would like to point it to you like for the inner ring regions, for example, the 7A and 7B regions, as you can see here for the 7B, we don't really see any pHs like when we move from the star-forming ring to the center, and pH features kind of get suppressed heavily in the nuclear spectrum, as you can see here. So in this diagram, I sorted the spectra in an order of using 6.2 to 7.7 pH features. As you can see from those three pop features that I am most interested in this study. Yeah, this is just to show a comparison between a nuclear spectrum with the spectrum that's extracted from the star-forming regions from region 1. So we can really see that like all of the pH features, including 6.2, 7.7, 11 micron, all get suppressed hardly in the nuclear spectrum.
Thomas, I just wanted to let you know you have about 5 minutes left before questions.
Okay, yep, thanks. Let me see. Right, so in order to study the PA variations, we have developed a tool that's using the, that's based on the cafe model that we have developed by Marshall in 2007. And using this tool, we are able to fit the emission lines, PA feature, and stellar and dust continuum simultaneously. And now we're currently in a active development in trying to apply this tool on the IFU cube. Yeah, this is just to show some of the cafe fit results from our extracted spectra. As you can see here, there's tons of different interesting diagnostics in the mid-infrared. And using this tool, we are able to separate all those lines in order to study the physics of the environment in the star-forming ring. So typically for POS studies, we use POS diagnostic tracks that give us an idea of how dust grains size changes and how its charge state changes in the environment. So in this study, we use strain 2021 results of the POS diagnostic plot here. As you can see, the x-axis, the larger the grain is, the smaller the ratio of 6.2 to 7.7 is. And if the grains are more ionized, we'll see a smaller 11.3 to 7.7 micron POS ratio. So here are just some of the comparisons that we get from the previous study in the past, including SINS galaxies and ghost galaxies. Yeah, and those are the final results of all the POS ratios that we had from our 18 regions here. So in the end, what we get from our study, the takeaway point is that we see the POS variations is mainly agree with what we found from the normal star forming galaxies from the Spitzer IRS results. And as we move from our aperture from the star forming ring to the center part, we see all of the regions show a larger grains distribution. So I think the main argument is that in the very center, we see that those grains become larger because the smaller grains are destroyed, can be destroyed by the AGN. So we also look into what really drives this variation of the grain size, and we're using the neon 3 to neon 2 ratio as a probe of the hardness of the radiation field. So I kind of see there's a correlation that when the radiation field is harder, only larger grains can survive and smaller ones may be destroyed. Yeah, so in our studies, we also look into H2 lines, which allows us to probe the temperature of the gas in the environment. And we see that there's we basically detect a suite of H2 pure rotation lines from S1 to S7. And using H2 to POS ratios, we're able to study the shock, use it as a shock diagnostic to study whether there's shock in this environment. But one thing that we found is that basically the star forming ring doesn't really get affected by the shock that much. So even though at the very center there's outflow from the nucleus, but it didn't really expand that further away to the star forming ring. Yeah, so here are some of the takeaways that we have from our study. The first thing is we showed that with JWST, we're able to resolve the ISM in this very interesting galaxies because it includes both an AGN and a star formation in this galaxy. And we can then, with the IFU, we can study them in detail. And we find that in terms of the POS properties in the star forming ring is basically similar than what we found from the nearby star forming galaxies in the Spitzer observations. And we see that the grain size distribution shift towards larger and in the inner ring regions. And lastly, we detect multiple H2 pure rotation lines, which we can use it to study the temperature of the gas together with the molecular gas mass in this galaxy. Yeah, so lastly, I would like to advertise for other papers that we already had from our ERS programs. So these are just the first batch 8 papers that we're that's gonna have in the archive. So if you're interested, please look into it. And then we're gonna have more interesting things coming out once we get our other observations. Yeah, I think I will leave my takeaways here and then take questions from you guys. Thank you.
All right, thank you, Thomas. If anyone has any questions, please go ahead and raise your hand. All right, well, if there are no questions, I'd like to thank both of our speakers again. And I'd like to advertise our next webinar in the series, which will be Monday, December 5th. And we will be skipping our webinar in January for the AAS meeting. So with that, thank you very much. And everyone have a great afternoon.
Thanks a lot, Nate.